Hey everyone, welcome back to another CIE A Level Physics past paper video. Today we're going to talk about paper 2, variant 2.2 from the February-March 2024 series. Before we jump into the paper, some resources, a great booster pack that we developed. Let's just show you. So this great booster pack, it's available on Patreon on the link you can see below the video and in the YouTube video description also. It's also available on our link tree, so you can see the link tree. You can also navigate there, but what it contains are certain documents such as AS definitions and formulae, so all the key terms and definitions. This is a table of reasonable estimates and it goes down all the way to particle physics. Frequently examined questions, paper 2 questions that come up frequently, some important questions also. We have important derivations. Some derivations are important, they come frequently. Then we have A2 definitions and formulae similar to AS content, key terms, definitions, key points. Then we have important derivations. Some derivations come quite a lot, for example this one comes quite a lot in different forms. Then we have graphs, field graphs versus potential graphs. Every student gets stuck on them, whether it's gravitational fields or electric fields. Then we have the most important one, the paper 4, A2 frequently examined questions. As you can see, you have syllabus content on the left side, question and answers on the following columns. And on the right side, you can see the years where they are most frequently asked. As you can see, for example, this one, this is not an exhaustive list of years, but this is quite sufficient to show you that this is a question that comes up again and again. Then we have paper 5 planning question. This is a checklist from the marking scheme and the syllabus. This is designed to have a sort of like a checklist or mental mnemonic, you can say, to help keep track of everything you need to discuss while planning your experiment. It also has some SALT past paper examples also from October-November 2024. And once again, this is all available on Patreon. Check it out. And let's jump into the paper. Question number 1. Table 1.1 lists some SI quantities. Complete the table by indicating with a tip which rows are SI base quantities. So we know what are base quantities: length, mass, time, current, absolute temperature or just temperature. Then we have amount of substance, mole, and luminous intensity. Okay, so current is a base quantity, energy no, force no, mass yes. Use the definition of power to determine its SI base units. Okay, so power is the energy or work per unit time. So work can be written as force times by displacement divided by time. Force units is in kg, meters per second squared, because this is MA, times by displacement M divided by time S. So this becomes kg meter squared S minus 3. Right, so this is it. Right, so let's write it: kg meter squared S minus 3. Right, A light meter is used to measure the intensity of light in a classroom. Daylight is incident normally on the sensor on the meter. Okay, sensor has an area of 22.2 centimeters squared. The reading on the meter is 950 watt per meter. Calculate the power of the daylight incident. So basically this is your intensity, right? So intensity is power over normal area or perpendicular cross-section area. So intensity is given as 950. Power is given, the area is given as, but we don't know the power. Area, we need to convert it into meter squared, so 2.2, 10 raised to the power minus 4. So hence, power would be 950 times by 2.2, 10 raised to the power minus 4. 10 raised to the power minus 4. So we get 0.209. So basically 0.21. Okay, so this was the first question. Let's move on to the second one. Question number 2. Define acceleration. Simple. Rate of change of velocity with respect to time. Okay, you can also call it as a ratio of change in velocity over change in time also. With respect to time just simply clarifies what the rate is between, because rate can also imply currency rate. However, even if you don't write this sentence, you will still get the required mark, but with respect to time clarifies what the ratio is between the two quantities. Okay, an Olympic diver stands on a platform above a pool of water. When the diver is on the platform, his center of gravity is at a vertical height of 9 meters above the surface of the water. The diver jumps from the platform with a velocity of 5.9 meters per second at an angle 60 degrees to the horizontal. Air resistance is negligible. When the diver hits the surface of the water, his center of gravity is at a vertical height of 1.2 meters above the surface of the water. Calculate the speed of the diver at the instant he hits the surface of the water. Okay, so initially he has 5.9 sine of 60 and 5.9 cos of 60 degrees. This one will stay constant, however the vertical velocity will change. What we basically need is the vertical displacement of its center of gravity. So 9 minus 1.2, 7.8 meters. And actually that would be negative 7.8. So we need to see final vertical velocity. V is equal to we can use v squared equals to 2as plus u squared, and we take upwards to be positive, so v squared would be equal to 2 times by minus 9.81 times by minus 7.8 plus 5.9 sine of 60 whole squared. So when we want the final vertical velocity, let's call it Vy. Okay. So 2 times by 9.81 times by 7.8 plus 5.9 times by sine of 60 whole squared. We get this value 13.384. Actually this is not the value that we want. So final speed would be Vy whole squared plus 5.9 cos 60 whole squared. So what we can do, this is your V squared plus 5.9 5.9 cos of 60, and we need to square this up also. Right, okay, so final speed V would be equals to 187.846, so we can round it up as 190. Sorry, no, this was the square, this was the squared. We need to square root this finally, 13.75. So therefore the V would be 13.7, so let's call it 14. Alright, the diver in B enters the water and decelerates. Okay, describe and explain the variation of the viscous drag force acting on the diver in the water as he moves downwards. Okay, so viscous drag force increases with velocity, and since the body or the diver is decelerating, velocity is decreasing, hence the viscous drag force will decrease. So the diver decelerates, causing a decrease in velocity. Viscous drag force which depends on velocity also decreases. Yes, that's it. Okay, the diver has a volume of 7.5 10 raised to the power minus 2 meter cube. The density of the water is this. Right, show that the upthrust acting on the diver when he's entirely underwater. Okay, so entirely underwater means that the rho GV is the entire volume. So rho is 1000, G 9.81, volume 7.5, 10 raised to the power minus 2. So 9810 times by 7.5 times by 10 raised to the power minus 2, 735, which can be approximated to 740 newtons. Right, okay. At a particular instant, when the diver is entirely underwater, his horizontal velocity is 0. Okay, the viscous drag force acting on him at this instant is 950 Newton vertically upwards. The diver has mass 78 kgs. Determine the magnitude and acceleration of the diver. Okay, so for example, this is the diver. The weight is 78 G. The viscous drag force is vertically upwards 950. This is the drag force, and there is this is the upthrust. Upthrust was 740. Okay. So we need to figure out what is the direction of the acceleration. Right, okay, so sum of forces equals to MA 950 plus 740 minus 78 times by 9.81 equals to, we Actually, we already saw that this was going to happen. However, what you can do is you can take 78g minus that also, ma. So a would be 950 plus 740 minus 78 times by 9.81 divided by 78. 11.86, you can call it 12, upwards. And that's it for this question. Let's move on to the next one. Question number 3. A thin metal wire X of diameter 1.2 10 raised to the power minus 3 is used to suspend a model planet as shown in figure 3.1. The variation with strain of the stress for wire X is shown in figure 3.2. Okay? The strain in X is 5.4 10 raised to the power minus 3. Calculate the force exerted by the wire on the model planet. Okay, all right. So if let's make this. Let's find out the stress from this, corresponding to 5.4 10 raised to the power minus 3. So 5.4 would be, if this is 5.24, this would be 5.4. So 5.4 is right over here, and this is this one. So 0.72 gigapascals. Okay. So stress is 0.72 gigapascals. You can also write it as 10 raised to the power 9 pascals. Okay, and we know that did they give us the cross-sectional area? Yes, 1.2 10 raised to the power minus 3 meters. Okay, area pi d squared over 4, pi over 4, sorry, what was it? 1.2 10 raised to the power minus 3. Whole square. Okay, so let's calculate that. So pi divided by 4 times by 1.2 whole squared times by 10 raised to the power minus 6. So we get this. Let's write in the standard form. You have 1.13097 10 raised to the power minus 6 meters squared. Right, okay. We're using more decimal places or more significant figures because this is not the final answer. We need the force, so force is going to be, we know stress is force over area, so therefore force would be stress times by area, 0.72 10 raised to the power 9 times by 1.13097 times by 10 raised to the power minus 6. So this times by 0.72 10 raised to the power 9, 8.143 10 raised to the power 2, so 8.1 10 raised to the power 2, or 8100. No, sorry, not 81, sorry, my bad, I misspoke. This is 810. So either you can write it like this or 810 newtons. The elastic potential energy of X is 0.31 joules. Calculate the original length of the wire before the model planet was attached. The elastic potential energy is this. We have the force. Do we know the extension? No, we don't know the extension. Right. To find out the original length, I think we can use Young's modulus. So FLAX. Or we can use the strain, but we don't know that, right? We don't know that. We can use the same strain. Yes, we can use the same strain. Okay, all right, we can do that. Right. Okay. We don't need this. All right. So energy, potential energy, is half times by Fx. So x would be 2 EP over F. 2 times by 0.31 divided by 810. This is our extension. 7654, 10 raised to power minus 4 meters. So strain is x over L, so therefore L would be x over strain. X is 7.654, 10 raised to power minus 4. Strain is 5.4, 10 raised to power minus 3. So this divided by 5.4 times by 1000. So this will get us 0.14 meters. Wire X is replaced by a new wire Y with the same original length and the diameter but double the Young modulus of X. Wire Y also obeys the Hooke's law. Okay. Now, double the Young modulus. So Young modulus is basically the gradient of the straight line region in the graph of stress versus strain. The straight line only. And if it obeys Hooke's law, that means we have a straight line region. Stress proportional to strain. So if it has double the Young modulus, that means that you have double the gradient. Okay? So double the gradient. Now, see the gradient over here. This is 3, rise over run is 0.4 over 3. We need to double it. This would become 0.8. So right over here, let's rotate this. Right, okay. That is, do we need to label it or something? Yes, okay, that's it. Alright, so that's this question. Let's move on to the next one. Question number 4. A nucleus P undergoes alpha decay to form nucleus Q. Complete the equation for this decay. Okay, so when alpha is mass 4, proton number 2, and we can basically see 215 minus 4, 211, and this would be 22. State the principle of conservation of momentum. Right, now we have two variants for this. Let me show you in the Great Booster Pack. Okay, two different versions, but almost the same thing, but two different phrasing over here. The main difference is the word isolated system and no external forces. So either you say isolated system or no external forces. But this is an important point. It's not just the total momentum remains constant or the total momentum before or after collision remains the same. This point, that this is an isolated system of interacting bodies or colliding bodies, or no external forces act on the system of the bodies, that is also important. So let's go back to the paper. So we can say that it states that the total momentum of an isolated system of interacting bodies remains constant. Okay, alright. Before the decay, the nucleus P has a speed of 3.2 10 raised to power 5. After the decay, nucleus Q is stationary. Calculate the speed of the alpha particle after the decay. Okay, so basically it is m1 u1 equals to m2 v2. No, sorry, v1 plus. Actually, this is m2. v2 plus m3 v3. Now masses are all in atomic mass unit, but we might not need that because masses are all in atomic mass unit. So nucleus P has 215 U times by speed is 3.2 10 raised to power 5, right. Then we have nucleus Q, which is stationary, but the alpha particle for U times by V. So as you can see, U and U will get cancelled, so V would be therefore 215 times by 3.2 divided by 4 times by 10 raised to power 5 is 1.72 10 raised to power 7, 1.7 10 raised to power 7. Alright, so that's it for this question. Let's move on to the next one. Question number 5. By reference to the direction of propagation of energy, state what is meant by transverse wave. Alright, so this is also a question that's given in frequently examined questions. However, let's simply answer this. Let me just show you. Okay, so as you can see, transverse wave is a wave in which oscillations, vibrations are perpendicular to the direction of the wave's energy is traveling. So, the transverse wave, we can reset that. A wave in which the oscillations are perpendicular to the direction of propagation of energy of the wave. Alright, okay. A space telescope is designed to detect electromagnetic radiation with wavelengths of the range 12 micrometers. So 12 micro, that means in this region, to 28 10 raised to power 6. State the region of the electromagnetic spectrum for this radiation. Although the answer for this is fairly easy, but let us show you what it means, what it actually means. So for example, if you convert this into nanometers, so in nanometers, 12 10 raised to power minus 6 times by 10 raised to power 9 is 12,000, right? 12,000 and 28,000. So basically this is the infrared range. However, let us show you in the Grade Booster Pack we have the ranges also. Right, so as you can see, if you want to convert the value that we had in that, so 1.2 micro divided by 12, my bad, I actually wanted to convert it into standard form. So you divide by 10 and multiply by 10 to do that. So this becomes 1.2 10 raised to the power minus 5. So minus 5 would be in between this region. Okay, so infrared. Now going back, infrared. Okay. A detector on another space telescope detects an electromagnetic wave. The signal from the detector is transmitted to Earth and displayed on an oscilloscope as shown in figure 5.1. Frequency of the signal displayed on the oscilloscope is equal to the frequency of the detected electromagnetic wave. The time-based setting on the oscilloscope is 5 10 raised to the power minus 15 seconds per centimeter. Calculate the wavelength of the detected electromagnetic wave. If it's an electromagnetic wave, the speed will be speed of light. So wavelength would be v over lambda. So, v over f or vt, basically time period, right? So we can do 3 10 raised to the power 8, and we need to figure out what's the time period. So time period, it's 4 1 2 3 4 5 6 6 times by, that means 6 centimeters, 5 10 raised to the power minus 50. So 3 times by 6 times by 5 10 raised to the power 8 minus 15. This is this value. Let's convert it into standard form. 9 10 raised to the power minus 6. Alright, so that's it for this question also. Let's move on to the next one. Question number 6. Coherent visible light of a single frequency is incident normally on a double slit. This produces a pattern of bright and dark interference fringes on a screen. Okay? There are 7 bright fringes. Explain how the pattern of bright and dark fringes is formed. Okay, so there are 3 points to this. One is the basic definition of superposition. Like although the light source is one, but it is diffracted and moves and behaves like 2 sources, and they meet, the diffracted light from the sources or from the slits, from the double slit, meets at the screens and interferes with each other or superposes at the screen. So that is point number 1. Second and the third point are why the dark and the bright fringes happen. So bright fringes happen when the phase difference between them is 0 degrees, or the path difference between them is n lambda, where n is an integer. Or you can also say half lambda, n times by half lambda, where n is an even number. And dark fringes happen when you have a multiple of 180 degrees phase difference, or n over 2 half lambda, n over 2 half lambda, where n is odd. This would be where n is even. So basically that's what we need to explain. So light diffracts at the double slit and meets at the screen bright fringes are formed when the light, we forgot about the superposition, and superposes to create an interference pattern. Bright fringes are formed where light from two slits have a phase difference of 0 degrees, and dark fringes are formed where light from two slits have a phase difference of 180 degrees. Okay. The distance between the centers of the bright fringe and the bright fringe Y in the pattern is 10.2 millimeters. So, okay, so you have 1, 2, 3, 4, 5, 6. Okay, so 6 units. Not bright fringes, 1, 2, 3, 4, 5, 6, 7. 7 bright fringes, but the distances between them, notice it's 6. So 1, 2, 3, 4, 5, 6. X basically would be 6. So X is basically 10.2 millimeters, or let's convert it into meters, divided by 6, okay. Slit spacing, which is A, distance from the slits to screen, that is capital D, right, okay. So lambda is AX over D. A is 1.2, 10 raised to power minus 3. X is this, 10.2, 10 raised to power minus 3, 6, and D is 3.1. Okay, so 1.2 times by 10.2 divided by 3.1 divided by 6 times by 10 raised to power minus 6. 6.58, 10 raised to power minus 7. We have 3 significant figures also in this, but mostly 2, so just 2. We can say 6.6, 10 raised to power minus 7. Okay, the light is replaced by a different visible light with a shorter wavelength. State how the new fringe separation will compare to the original fringe separation. So as you can see this, lambda is proportional to x. If you have a shorter wavelength, the fringe separation will be shorter. New fringe separation will be smaller. Okay. A stationary wave is formed on a stretched string AB. Okay, PQ and R are points on the string. On figure 6.2, draw a cross to show the position of the nodes. The nodes are where you have these, and this. State the phase difference between P and Q. So in between the adjacent nodes, the phase difference between the particles is 0. But in between adjacent node pairs, like in between this and this, you have 180 degrees phase difference. And that's it for this question. Let's move on to the last one. Question number 7. Define electric potential difference. So this is just work done or energy transferred from electrical to other forms per unit charge. Right. So you see this in the frequently examined questions. So the electric potential difference between them is between 2 points is the amount of work required to move a unit of electric charge from one point to another, or across a component, or between 2 points is the energy transferred from electrical to other forms per unit charge. So it is the work done or energy transferred from electrical to other forms per unit charge between 2 points in a circuit. That's it. Okay. A cell of electromotive force EMF 1.8 volts and the internal resistance R is connected in parallel with a resistor of resistance 6 ohms and a filament lamp. Switch S is open. The ammeter reading is 0.25 ampere. Determine the internal resistance R of the cell. Okay, so we use the Kirchhoff's laws. Second law over here. So basically you have EMF, which is 1.8 volts, equals to I times by R plus 6 ohms. Okay, so I R plus, oh sorry, we already have 0.25, right? So, sorry, I forgot. So 0.25 R plus 0.25 times by 6. So R would be just simply 1.8 minus 0.25 times by 6 divided by 0.25. So 1.8 minus 0.25 times by 6 divided by 0.25, 1.2 ohms. Okay. At the time t1, switch S is in figure 7.1 is closed. Figure 7.2 shows the variation with time t of the ammeter reading I. State whether the EMF of the cell after t1 is greater, less than. So EMF is not changed. So EMF remains the same. It's the terminal potential difference that might change. By considering the effect of the lamp on the total resistance of the circuit, explain the variation of the ammeter reading shown in figure 7.2. Okay. So basically we have to explain the entire variation. So basically why the current jumps and then why it gradually declines like this. So why does it increase? Because of the sudden drop in net resistance, because as you can see, this and the 6 ohm resistor are in parallel with each other, so the net resistance of the circuit is decreased, so that there will be a sudden jump in the current. However, we know that the filament lamp is a non-ohmic device. As temperature increases, the resistance would increase. That means the current would start to decrease. Okay, so that's the explanation for this. The current initially increases due to a sudden decrease in net resistance of the circuit as a lamp and 6 ohm resistor are in parallel. The current flowing through the lamp causes filament to heat up and cause the net resistance of the circuit to rise gradually. This causes, actually this was a period, this causes a gradual decline of current through the ammeter. That's it. And that's it for this paper also. I hope you enjoyed the explanations. If you have any questions or doubts, feel free to reach out. I would love to help you. If you think I made a mistake somewhere, although I'm going to make sure that I don't, please also reach out in the comments, point out any confusion you have. Do check out the grade booster pack that we showed you. This is available on Patreon. As you can see, that we used it a couple of times, so this will be immensely valuable in your final revision. And hopefully we will see you in the next video. Meanwhile, take care. Bye bye. Oh, and don't forget to give this video a thumbs up, subscribe to our channel, and turn on the notifications for future updates. Bye bye.